So just say when, I guess.
You are online.
I'm online. We're recording?
Yes.
Okay, then go ahead and have a seat,
Sure.
and we'll just get started. Here, let's get that cursor out of the way. There you go. So, my name is Dr. James Nagel. I actually got my PhD here at the University of Utah, and it's actually been so many years I forgot when I got my own PhD. I think it was 2012-ish, 2011 when I graduated. So my background is mostly applied electromagnetics with kind of a specialty with numerical methods and a little bit of signal processing thrown in. My specific kind of PhD topic was light trapping in silicon thin film solar cells. And so that gave me a lot of background in just kind of the problem of solar cells and where the efficiency is and how to trap light in them. And it's very relevant to this class because optics for energy is the name of the class, right? So you guys sound like you do a lot of exactly that kind of problem of how to use light to make energy or facilitate energy generation. And I guess we'll just go ahead and get started. Most of you guys have told me you're mostly material science background, so how do I switch slide? Spacebar? Or do I just click? There it goes. So you're mostly material science. This is kind of an E&ME, ray optics, radiometry kind of lecture topic, but we'll try and kind of keep it as high level as we can. Most of this is just kind of for fun and edification because Dr. Manon is not around. So let's just kind of jump into it and talk about the problem of light trapping and why it's important, what its applications are, and what are some of the research areas you can worry about or get involved in as you get into your graduate studies. But light trapping is essentially exactly what it sounds like. Here is some thingy in space. I just kind of drew a little circle. And you imagine some ray of light coming in and pinging into it, and it bounces around inside, and eventually it will absorb inside that object. So and that's what you would mean by trapping. It doesn't matter how or when it gets absorbed, just as long as it doesn't leave the object at some point or maybe bounce off of it like in a reflection or a scattering event. So we kind of want to make little black holes in a sense, light enters and nothing leaves. So one of the most important metrics in light trapping is this idea you call light trapping efficiency, or another word you'll hear us thrown around is this absorption factor. And it's just essentially the ratio of how much energy does this thing absorb in itself, how much light, divided by how much actual energy struck it, okay? So if I had like perfect light trapping efficiency, then all the energy that hits this thing would be absorbed inside of it. If I had no light trapping efficiency, it could enter it and bounce around and then leave, or it could just reflect outright or maybe even miss it entirely. And it's kind of however you need the application specifically to measure that parameter. Okay, so a lot of what we're doing in light trapping is all about capturing light. So why would I want to capture light? Can you even see that slide? This is all dark. Is there a way to turn up the brightness? Well, it looks really bright here on this screen. So I hope the recorded lecture looks really good, because I'm probably doing a screen capture, not projected. But so you see over there on the top left, there's an F-117. So that's kind of the quintessential light trapping problem, in a sense, is stealth. Not exactly light trapping in a sense. It's mostly, you remember the idea of you have a radar station, it's sending out a really powerful signal, some pulse of light, and you're listening for echoes. So there's two ways to avoid creating echoes. One is you can just scatter all the light away from the source. So you're not really absorbing any, you're just bouncing it away in such a way that the sender doesn't hear any echoes from you. And part of that is all built into the geometry of the plane itself. But you can't really guarantee that all the energy is going to scatter away from the source. So what they kind of do to compound on top of that is they build the plane out of this sort of, they'll paint it in this sort of magic black material. And, you might have seen those documentaries on, like, Discovery Channel where they always talk about their fancy radar-absorbing paint, right? So if you're not going to scatter energy away from the source, you want to maybe at least just absorb everything that hits it. So it's kind of a two-pronged approach. So that is, in a sense, a light trapping application. Any light that kind of gets into the plane If you can't scatter away, you might as well just absorb it entirely. So this picture here on the bottom, you probably can't see it at all. It's all blackened here. But it's an anechoic chamber. So, I don't know, maybe you can kind of see here. So it's right there. You can see this little orangey thing. That's an antenna. We're trying to measure its directivity pattern. And the idea of an anechoic chamber is I want to mimic a perfectly free space environment. Because when I measure the directivity of an antenna, any sort of reflections off stray objects will screw up that measurement. So what they do is they have this big metal chamber, and you can't really see it, but there's these little cone foamy thingies poking out of the wall, and they're designed to minimize echo. So energy will come in, it'll kind of interact with the antenna and scatter away, and without that foam, it would bounce off the walls again and come back to the antenna and screw up the reading. So we want all that energy that hits the walls to be absorbed or trapped, right, light trapping, so that you have no echo. So that's why it's called an anechoic chamber, a non-echoing chamber. So that's another sort of application of what light trapping might involve. For you guys, you probably know exactly what this picture is up here, and that's solar cells, of course. This is probably the application you're mostly interested in optics class. The other two are mostly kind of RF, radio, radar-related antenna theory. So in a solar cell, the idea is essentially the same. I have all these photons landing on some aperture, some panel, and I want them all to be absorbed. I don't want them to pass through. I don't want them to reflect away. I want to trap them somehow and convert them to usable electricity. So that is the application we're going to really heavily focus on for this lecture. So let's just give a little background in solar energy. This is a really fun slide because it shows a mapping of kind of the solar energy resource available across the continental United States. So you look down here at the units is kilowatt hours per square meter per day. And it's compiled by the National Renewable Energy Laboratory, or NREL. And I think what they're doing, they actually account for things like cloud cover, not just latitude. So that's why Florida here isn't quite as good as, say, Arizona, New Mexico, because they get a lot of rain out there. So yeah, it's very sunny and hot and low in latitude, but the climate in that general area is cloudy too, so that kind of works against them. So why is this important? Well, you know, we need electricity. We like to keep our lights on. We like to run laptops and drive cars. And that demand for energy is just exponentially growing by a few percent every single year. So we need new sources of energy to kind of keep up with that. And then, of course, there's that pesky issue with fossil fuels and carbon emissions and global warming. So we'd like to try and find sources of energy that aren't going to release carbon dioxide. So this makes solar power very attractive. You just whip out these little panels and build them out in the desert, and it's just free energy falling from the sky, in a sense. So this might raise a question. Why haven't we just flooded the Arizona desert with solar panels yet? You know, what's the holdup? There's the technology right there. There's a picture of it happening right now. So why aren't we making millions and millions of those things? So throw out a guess. Why haven't we done that yet? Infrastructure.
Reliability, solar power.
Cost is actually one of the bigger ones here. But you're right. There's also issues of if I'm generating power here in New Mexico, I can't exactly deliver it very easily up to New York, right? But then, you know, that would say, well, maybe that's good for New Mexico. Why isn't all of New Mexico just running off solar power then? So, you know, but you still have the issue of maybe storage and, but you know, what do you do when it's cloudy out? But like you said, really cost is one of the major drivers in all of this. You know, even if we could kind of solve all those problems, it wouldn't necessarily help us if it's too expensive to just make the thing. So why build one solar farm when I could make 10 coal plants for, you know, half the price? So a lot of what we're going to talk about is just kind of the economics and technical difficulties with making solar cells cheap. So the industry goal, it's fun actually giving this lecture every year because about 2012 or so, there was this big goal where the industry set where they wanted to get $1 per watt of solar energy cost by 2017. And 4 years later, they're actually getting very close to that. You can see the cost of solar cells back then was about $5 per watt, and now in 2016, we're down to about the $2 per watt level. So we're not quite at the industry's target yet. It kind of stagnated here, but there's been a lot of progress. So obviously, as the price of solar installation goes down, the total number of solar installations is going up in proportion. And that's really good. We like that. We want to see that trend continue. But if you really want to see solar cells kind of on a competitive, equal market footing with, say, coal power or natural gas, that $1 per watt is really kind of what people have accepted as the goal, the threshold that we have to meet. But that's okay. We're getting there. We won't hit it in 2017, but maybe we'll hit it in 2020. Or maybe somebody in this class will come up with a way to really help push that target. Okay. So the question we might be asking is, why aren't we there yet? What's the holdup? Why are solar cells so expensive? There's actually a lot of reasons for that. Like you said, there's installation cost, balance of systems cost. When you put solar panels on your roof, you have to pay some person to come and install them. If you're going to do tracking, you might need some tracking mechanism. You need some integrated system that will plug it into your wall, and it's complicated. And every one of those things adds cost. So people have made a lot of progress, like in standardizing the parts and the labor. That helped a lot with the cost, and just economy of scale has helped a lot. But for a while, a big problem was just the raw cost of the silicon itself, it turns out. So just a sidebar, silicon is like by far the dominant material in solar cells right now. It's not the only one. There's a lot of other kind of competing materials out there that you'll find. For example, cadmium telluride was a popular material for a while. But silicon really is kind of the number one that everybody would love to see dominating the market or taking over the market entirely for solar cells. There's a lot of good reasons for that. So silicon is very abundant in the Earth's crust, at least. And it turns out you can make solar cells that are really cheap and awesome out of other materials, but you can't make 10 billion of them that would supply the United States. So that abundance of the material is actually a huge push for why everyone really likes to see silicon-based solar cells. The toxicity of silicon is not so bad as other materials. For example, I think something like 1/4 of the Earth's crust is some kind of silicate-based molecule. So apparently it's not poisoning all our drinking water, so you can kind of crunch these up and throw them in a landfill, and there doesn't seem to be any immediate environmental worries along those lines. It's fairly easy to mine and process. It has just the right band gap for pretty good efficiency. And of course, for the last 50 some odd years, we've been making all these really fancy computer chips in a multi-hundred-billion-dollar industry. So we're pretty good at making silicon do things already. So there's all these reasons we like silicon, and we're trying to make it kind of the big, that's why it's kind of the go-to material for widespread solar cells. Now, there is something to kind of bear in mind. When you break down a silicon solar cell, I guess just kind of sidebar, how much have you guys talked about, like just the raw, I guess, design of a solar cell? Have you messed around with that at all? How do you make a solar cell at the end of the day? Have you talked about that much? Okay. So this diagram here is fairly familiar to you guys. You have a piece of silicon, and it's p-type doped here, n-type up there, and you have kind of these, you can't really see it, but there's these little islands of p doping on the bottom here. And the idea is, I wish you can't really see, but here's a ray coming in from the top, and that's where it's being absorbed, and you create an electron-hole pair. And you can't see, but there's this little sort of Brownian motion where the electron wanders to the n-type, and the hole wanders down here to the bottom. And that is an excited particle that can be used to do work. Now, the idea to impress, though, is that most of this solar cell is just a big giant chunk of silicon with some magic doping and materials slapped onto the top and bottom. But it turns out that raw mining of silicon in that solar cell is a big chunk of the cost. Or at least it was back in like 2012. I don't know if the situation's changed a lot, but just that raw slab of silicon, that wafer, is actually pretty expensive. So let's kind of throw some numbers at this. Okay. So this is a diagram of a solar cell that was made in 1999. So at the time, this was like the world record holder for solar cell efficiency in a laboratory setting. And they pulled out all the stops and made a 25% efficient solar cell, which is actually really, really good. I don't know if it's probably been beaten, but if it was beaten, it would only be by like 0.1% or 0.5%. If I had to guess, the world record holder today is probably like 26%, or not 25. So this is a pretty good representation of how to make a really awesome solar cell. And the key metric to bear in mind is, for most solar cells, this layer here, this wafer that you had to use to cut out of silicon, might be anywhere between 150, 250 microns thick. And this particular example, I think they made it out to 400 microns. And that doesn't sound like much. It's 0.4 of a millimeter. But it turns out, economically speaking, back in 2012, that bulk silicon, just the wafer itself, was anywhere between 1/3 to 1/2 of the total system cost of the entire solar cell. Just the raw bulk molecules or atoms of silicon that had to go into the thing. So that motivated a lot of people to rethink how we design solar cells. Because, let's click here. So what you're seeing here now, this was a solar panel you could just buy off of Amazon back in 2013 or so. And looking at the raw numbers, you could get like 12% efficiency, and it was $5 per watt. And you can see how they made it was individual wafers were all kind of ganged together. And so you can see there's a lot of horrible manufacturing costs and material costs that went into that. Because essentially someone almost by hand had to gang these together and connect them or create some process that did that. And it was just complicated and clunky. And that's why these things were generally expensive. But in particular, like I said, it's just this bulk layer here of silicon was a major source of cost in that solar cell. So that motivated people to consider what are called thin film solar cells. So instead of hundreds and hundreds of microns thick, they brought it down to, why not, 1 micron or 2 microns. So that whole material cost that went into just collecting the atoms of silicon went away. Instead of, $2 per watt out of just the raw silicon itself, that cost became 2 cents. So maybe instead of $5 per watt, you're now down to like $3 per watt just for this sort of change. And that's great because a lot of advantages come when you go thin in your solar cell. For example, you notice the last one, it was like little wafers kind of ganged together. When they went thin, there's deposition techniques that allow you to essentially print it in these rolls, almost like it's newspaper in a sense. So a lot of the manufacturing cost just plummets when you go to these thin film techniques or thin film designs. So this was another one I found off of Amazon at the time. Notice it says amorphous silicon, so it's not crystalline silicon, so it is kind of apples to oranges. But you'll notice it was only 6% efficient, but just the manufacturing cost was so low, it actually came out ahead at only $3.50 per watt instead of $5 per watt. But then that kind of raises the question, where did all that efficiency go? Why is this only 6% efficient, whereas before it was 12% efficient? And again, I'm doing kind of apples to oranges because this is amorphous silicon and not crystalline. But there are a lot of advantages to going to crystalline silicon. And I believe you can find kind of thin film crystalline solar cells today. So that'd be an interesting kind of lookup project sometime. But the problem with going crystalline silicon very thin is you lose a lot of absorption efficiency. You suddenly find yourself not being able to collect all the light. So this is a little graphic I kind of put together to represent what's happening. So you look at this green wave here. This represents 500 nanometer light. And this is actually kind of a calculation I did from the material properties of crystalline silicon. And you'll notice the distance here, the thickness is only 2 microns. So before it would have been 400 or 100, or only 2 microns. And for green light, that's okay. You see the envelope of the wave decays to, 98% absorption efficiency, and only a tiny little bit would come through out the other end if I made something like this. And, I'm ignoring reflections and things, but this is just for illustrative purposes to show the relative strength of absorption at different wavelengths. So by comparison, you inject red light at, say, 800 nanometers, and there's this huge dramatic difference now. I only scratched the surface on this wave here. Maybe 10% of that energy was absorbed in those 2 microns. So this is why we see a major drop in efficiency when we go thin, is because there's just not enough bulk material to capture all the energy, or to capture all the photons. So that leads us to the problem of light trapping. How can I still get light to stay inside of this thing and be absorbed and make electricity when it's just not enough material there to capture all the light? So that's the main challenge of light trapping in thin film. That's the key word, thin film silicon solar cells. So, okay, this graphic kind of gives a quantification of just how bad gets in capturing photons in silicon. So what you're seeing is called the absorption length. So that's sort of the 1/E decay length. You can also think of it as like a skin depth. So down here at 500 nanometers, the absorption length is less than 1 micron. Okay. 10 to the 0 there. So it's like 0.8 microns is enough to capture like 66% of the energy. So at 1 to 2 microns, you're actually capturing most of it. Then we go up a little to 800 nanometers. You notice this is a logarithmic scale, so a little change makes a big difference. Now all of a sudden it's more like 10 microns. And the band gap for crystalline silicon is way out here at 1100, now, which means you're way at like 100 microns of thickness just to capture 66% of the energy. So that is our problem. We want to deal with this end of the curve here somehow. And for kicks and giggles, also threw in gallium arsenide, and it kind of follows the same trend. As you get closer to the band gap, your absorption length suddenly skyrockets. So let's quantify that a little bit even further. So this is a really fun plot. If you ever do anything involving solar power or global warming or whatever, this graph is going to be extremely useful to you. So this is called the AM 1.5 solar spectral reference. And it needs a little explanation to sort of appreciate what you're looking at here. So that 1.5 is important. So we'll kind of explain it in layers here. So if you go to like the NREL's website, they have these databases of these solar references. So there's the AM0, AM 1.0, and then AM 1.5. So AM0 would be imagining yourself sitting in a satellite and looking at the sun and asking yourself, what's the average sort of daily energy I receive from the sun without any atmosphere to get in the way? Does it make sense? Or another way to kind of think of it is if I'm standing on the surface of the Earth and there's no atmosphere and I'm just kind of looking at the sun, how much sunlight would hit me over the course of a day? That's kind of a way to think of it. So then you have the AM 1.0, which represents what happens when an atmosphere is suddenly included. And that is a major reason why you see all these little absorption troughs, absorption lines everywhere, is because there's a bunch of water vapor and absorption just due to the atmosphere itself. So I'm pretty sure most of these are just because of the moisture in the atmosphere, but there's probably, I'm not a spectroscopist, so I don't know, say, what that particular line is all about. This is what you say when you have to look at sunlight through the atmosphere. There's just, you get all this absorption in the air itself. So that's just energy. If you had a solar cell, you would never be able to see it. It's just the air would take it away from you. And then you have this AM 1.5. So in contrast with the AM 1.0, 1.5 says, what if I'm kind of in North America? So the sun isn't really directly overhead all the time, but it kind of follows this sort of angled path a little bit. So instead of traveling through, this much air directly overhead, I have a little bit more air due to the fact that the sun is kind of out at that angle. And so you lose a little bit more energy just in the atmosphere because of that. So what the AM 1.5 spectral reference represents is what would the average person somewhere in the continental United States expect to see if they had a solar panel kind of tracking the sun? Okay, that's the idea. So you'll see this spectral reference thrown around a lot in the literature because it makes kind of a nice, handy representation of data for what we, as people in the U.S., can expect to gather with solar farms out here in the continental United States. So does that kind of make sense? That was probably a lot to swallow. So you notice I put here the band gap for crystalline silicon, 1120 millimeters. So all the photons, all the energy to the right is totally useless to me. No matter how much energy I collect or there is from the sun, I'll never be able to really gather any electricity out of this energy in this part of the curve. Only the photons to the left of that line have enough energy to excite an electron-hole pair in my silicon solar cell. Now, you might notice the units on this graph are a little funky. So you notice it's photons per second per square meter per nanometer. So it's a power density spectral density. And what that represents is, imagine an aperture, 1 square meter. I'm kind of holding it up and collecting energy from the sun. And I'm counting photons per second through this thing. But it's also a spectral density too, so in order to get actual photons per second, I have to integrate over some kind of finite wavelength bin. So if all the energy were concentrated at a single wavelength, it would just be photons per second per square meter. But it's spread out over lots of wavelengths, so you have to kind of account for that too. So it's a little goofy, but basically the idea is that the total area under this curve would represent photons per second over a square meter aperture. Okay. Now, why would I express this as photons per second instead of just watts? That's true. Every photon will have a different energy. But I could say do watts per nanometer in a sense. So watts per square meter per nanometer, and I could integrate over those wavelengths at different energies. So you're on the right track though, but there's an important reason why photons per second is really more relevant than photons per second per square meter as opposed to watts per square meter. And so the question is, imagine a photon right here at the band gap is absorbed in a crystalline silicon solar cell. What happens? It excites an electron into a higher energy state and leaves behind a hole, and those two particles drift away and do work. Now imagine the exact same scenario, but instead of here at 1100 nanometers, I come down half to, say, 650 over here. Now what would happen when a photon is absorbed? It's not a rhetorical question. Shout out the answer if you know it. Or what do you think? Yes. Yes. So you have the band gap, and it excites the electron, but it doesn't just go to the bottom of the next one. It goes way, way above, and then drops back down to the bottom of that energy state. So all the extra energy in the photons here is actually not really useful to me. So when I measure light trapping, it's not really a fair measure to say I've captured all of the energy, because I actually can't. If I had absolutely perfect light trapping, I wouldn't actually convert all of that energy into electrical work. So to measure light trapping, it's better to say I'm capturing all of the photons, and then I figure out how to make use of all that energy later, rather than collecting all of the energy sort of up front. Does that kind of make sense? So perfect light trapping means I'm capturing all of the photons, but not necessarily that I'm converting all that energy into electrical work, in a sense. That's kind of what this, why we use these units here. They're a little more meaningful to express it this way. Okay, so the idea is all the area under the left side of this bar here, and this curve, this is what I care about. If I want perfect light trapping, I really only care about this bit of the curve, and I don't care about over here, because these photons are useless to me. Even if I did capture them in some sense, I can't really do anything with them just by the physics of the solid state, whatever. So let's let's do some calculations. This is actually a pretty straightforward calculation you can do using some basic electromagnetic wave theory. So you imagine a planar structure here, and I'm shining light down on the top. So that's what this little squiggly photon here represents. And it hits the boundary here. A little bit of light will reflect, then some of it transmits through, and we're going to bounce off the bottom contact here, and then reflect back up, and then a little bit will transmit through, and then a little bit more will reflect again, and if you solve for everything, you'll get some kind of standing wave-ish pattern, where more or less energy will be absorbed depending on what wavelength you're at and the dielectric properties and so on and so on. But it's a pretty straightforward calculation. If I know the dielectric properties of silicon at that wavelength, then I can tell you what fraction of the incident energy will be absorbed in it at that wavelength. And then you just calculate again and again at all the wavelengths across the spectrum that you care about. So here is the black curve represents my AM 1.5. Those are the total photons available that I care about that nature is giving me. And this red curve tells me how many of them I would actually absorb in silicon if I made a 1 micron slab like this with a little metal back contact. So all these little peaks and troughs, those are called Fabry-Perot resonances. I don't know if you guys have talked about that in this class. Okay, well, fun fact. So what you do is you calculate the area under this red curve, and that tells me how many photons am I capturing, and then I compare it to the total photons available, and you find that we're only getting like 27% of the total light. So 1 out of every 4 photons that hits this thing will be collected, and the other 3 out of 4 will just bounce away, never to be seen again. So obviously that's terrible. We'd like to do better than that. Remember, not only, there's efficiency on top of efficiency. This is just my ability to collect the photons, let alone convert that energy into usable power. Okay? So the first step, you might say, okay, let's put an anti-reflective coating on it. And this is very common in solar cells. So there's no initial reflection, just the photon comes down, it'll pass through, get absorbed a little bit, bounce off the bottom, get absorbed a little more, and then leave through the top. And when you do that calculation, we get this little solid black line here. You notice all those little resonances went away, but I also collected a lot more area under this curve, and we suddenly find we're getting about 40% of the total energy. So it's a little better, but it's still kind of terrible. It's over half my photons are still just kind of entering and leaving. And you also especially notice it's really bad as I get out here towards the longer wavelengths. In fact, you get up very close to the band gap, and almost nothing is really being absorbed. So I'd really like to do better than that. So if you ever get involved in light trapping in silicon kind of solar cells, a common idea that will get thrown around is called the Lambertian limit, or the ergodic limit, or the Jablonovich limit. Everybody kind of calls this by different names, but they're all sort of the same thing. And the idea is, instead of just light passing down and back again, what if I add a bunch of bumpiness on the surfaces so that light doesn't just take these straight lines, but maybe gets scattered every which way? So the idea, for example, is you consider this little ray, instead of propagating down and back 2 microns through the material, it goes at this angle, and maybe it goes a total of 3 microns through the material. So the idea behind light trapping is, instead of just propagating up and down straight, I want it to go sideways. So I maybe only have 1 or 2 microns of thickness this way, but I've got feet of thickness the other way. So anything I can do to make these rays go sideways instead of up and down means I have essentially infinite depth of material to go through. And that's really all light trapping boils down to. I want vertical rays to kind of go horizontally, because eventually they'll be absorbed the more sideways they can go. I have infinite depth in those directions, but not an up and down. So it turns out, really the best you can kind of expect to do is called Lambertian scattering, and it's kind of this cosine theta dependence. We'll talk a little bit about that in more detail later. And what you see now is this blue curve. If you could do absolutely perfect Lambertian scattering, and you do the math and you see, wow, it's actually 81%. So a lot of people like to tout this as sort of like the best capturing that nature will give you. It's not really a hard fundamental limit, but it is kind of a practical limit that a lot of people will talk about. So you see it thrown around in a lot of papers, and every now and then somebody will brag like, ooh, we beat the Nov8 limit in our solar cell. And usually it's because they did some weird cheating thing where they only made it like 100 nanometers thick, and they only excited it with like one specific wavelength and did some weird photonic crystal thing. And you're like, yeah, you beat the limit at that wavelength, but now do it at all the wavelengths across the solar spectrum, and all of a sudden you find it didn't work very well. Or maybe it's just so thin that, yeah, you beat the limit, but it's just so ridiculously thin you still can't do anything with it. You have like 1% efficiency at the end of the day. So those are some little tricks people do. You know, they're showing off, we beat the limit, but there's a lot of practical issues that kind of, I guess we'll say baggage that gets carried on top of that. So for all intents and purposes, this 81% is kind of accepted as about a practical upper limit. This is about the best you can do. It's not a hard limit, but it is kind of a practical limit. So what our goal is here is to figure out how can we take this 40% curve and kind of push it way up here towards the 81%. So that's essentially what light trapping in thin film silicon solar cells is all about. How can I approach this curve here? Because that's about the best you can expect to do. So this was a fun slide. When I first started doing my PhD, this was like a really hot topic. Everybody was obsessing, how do we trap light in solar cells? We had all this thin films. What are we going to do? What are we going to do? So every other week, somebody came out with some wacky publication. And so you can see, you know, like they have this weird Bragg grating here, or some reflections in the back contacts, or you notice they do kind of like the anechoic chamber cones on the top surface in this guy here. My personal favorite was the surface plasma. I don't know what people were thinking with that, because superficially, I guess in hindsight, it seems like a really terrible idea. But at the time, it was really hot stuff because nobody had really fleshed out all the theory of this. But there's this weird idea, if you put little gold and silver nanoparticles all over your solar cell, then, you know, people were squeaking out an extra 5 or 10% efficiency in their light trapping. But then there was also the problem of you have a big giant hunk of metal on the surface of your solar cell scattering light away. So, I like to make fun of it. You know, I probably shouldn't, but this was a big deal in my research. This is why I got brought into this topic. Professor Scarpolo wanted to get involved in the light trapping business. So a lot of my research was running simulations and trying to figure out all the physics of this stuff. And this was just one of those things where I saw this, and just in the back of my mind, I knew that's never going to work. So sorry, I'm picking on them a little bit, but it's sort of a personal tease of mine. So let's go into kind of the physics of what's going on and how we can kind of quantify light trapping. So this idea came about of what's a nice way to sort of represent light trapping in an intuitive sort of sense. So people came out with what you call the Model N slab. So the N means no reflections, and it's kind of like that graphic I showed you before, where a ray comes in, it gets attenuated a bit, and then some of it leaves out the other side. So if there were no reflections, how much energy would be absorbed inside of that slab? So you just do a little bit of power balancing. The absorption, and these are fractions. So the fraction of absorbed energy is the incident, which is 1, minus reflected, minus transmitted. Okay, so I would have some energy here, some would reflect, then I would absorb, and a little transmits out of the side. And all of that has to add up to 1. And so I'm just solving for A, the absorbed fraction of that. And I'm pretending there's no reflection here. So I'm ignoring the reflection at this boundary and the reflection of this boundary. What's the equivalent length of material that this ray propagated through? So the transmission out the other side just follows this exponential decay. And so when I solve for absorption, I just have 1 minus t, which is 1 minus this e to the minus alpha term here. That's all it represents. So why is that interesting? So what you do, oh dang it, I updated this slide and I forgot to put it on the on the new thumb drive. Sorry about that. So what you do is you solve for the thickness and you get this negative 1 over alpha natural log blah blah blah. That's the solution for the thickness there. So what that means is I have, in a sense, an expression that tells me how much material did that ray propagate through in terms of its inherent absorption and material absorption properties, and maybe even some other geometric considerations. And I would solve for this little term here, and they would call it L, for an equivalent path length. So the idea is if I hand you a solar cell and I tell you, well, it has this much of an absorption factor, and this is the material's absorption coefficient, I solve for this L, and I would say it is as if all of the light passed through 10 microns of material. Even though the material itself might only be 2 microns thick, it may bounce around a little bit inside for a full 10 microns. So that's the idea of this equivalent path length. And you'll see that word smeared all around the literature, path length enhancements and equivalent path length. But it all sort of boils down to this equivalent slab of material and how far would you have propagated through it in this sort of abstract sense. So I'm sorry, I corrected this slide 20 minutes ago before I came in, before I got to put on the thumb drive. So we'll go back to this 1 micron slab here. It turns out you can express it in terms of these equivalent path lengths. So for example, the simplest case was, you imagine the antireflective coating at the top. An array will come down, it'll travel through 1 micron, hit the rear, and then travel through another micron and leave. So it's as if the slab were twice as thick. So you'd say it had a path length of 2 times W. So this is how you think of it. So the L is the equivalent path length, and W is the thickness of the actual slab. So the equivalent path length would be twice that. A fun fact is when you have the Fabry-Perot resonance effects, you get a lot of weird constructive and destructive interference going on, where it's as if a photon will come in, bounce around 2 or 3 times, and then finally leave. So you might actually get a lot extra path length enhancement. Or at other wavelengths, the exact opposite happens, where they'll come down and reflect again and constructively interfere out, and it's as if it actually has terrible path length through it. So that's what you can actually solve for those limits in this Fabry-Perot resonance here, and you find that the minimum, it actually divides it by the index of refraction, and then the maximum will scale it up by the index of refraction, which is kind of a neat effect. And when you plot the envelope, they actually have this nice, neat enclosure here. So that was a fun curve to put together. But so you can see the physical slab is only 1 micron, but depending on the wavelength, it's as if the photon traveled through 3 or 4 or 5 times as much thickness, or maybe even hardly 1/2 the thickness at all. So now the rest of this lecture, we're going to derive the Lambertian limit. And again, this is one of those little peeves of mine, because when I got into this was an idea people were throwing around like it was gospel. But the derivations for it were really counterintuitive and weird. You would have all these kind of arguments based on density of states and probabilities of photons getting in and out. And nobody ever just did a straightforward analysis of here's a photon, here's a ray, here's where all the rays are going and how much of them are being absorbed. And that bugged me for a very long time, because it's more intuitive to me to think of it that way than to do these weird roundabout density of states and quantum mechanical, statistical mechanic kind of arguments. So that's what we're going to talk about here, is that derivation. I'm actually debating, I have kind of a half-written tutorial I might put up someday. This is one of the things, people sort of know it, but they don't, and I think it would be good to kind of get that out there. So the idea is, we're going to assume a ray coming in and striking the top of this solar cell. And it could, in principle, come from any direction, because we're idealizing the antireflective coating. And we're going to idealize the surface here by saying it's a Lambertian surface. So another quick question. Does the word Lambertian mean anything to you guys? Are you familiar with that term? You have a whole class called Optics for Energy, and you haven't done any like Lambertian type radiometry? Okay, well, we'll just take it as gospel then, that the directivity of this energy in a Lambertian surface is this cosine dependence here. And it turns out there's a lot of cool things you can explain when you figure out this little cosine dependence. For example, this wall here looks white, and you would say, how bright does this wall look? You know, you could measure what you call a brightness on this wall. And if I look at it at this angle or that angle, it looks at about the same brightness at all angles. And an ideal Lambertian surface would appear equally bright no matter which angle I'm kind of looking at it. And it's that cosine dependence there that sort of gives rise to that effect. I saw one book saying this is actually why the moon appears to be like a singular bright disk in the sky, because it's very highly Lambertian. even though at the edges of the disk, you're actually looking at sort of this curved slope horizon at an angle. Yet, so why doesn't it look dimmer or brighter? And it's because of this equal brightness idea in Lambertian scattering. So this is, if you ever get in like a class on radiometry or something, this idea of a Lambertian surface is a big, big, big deal because most rough surfaces tend towards this cosine dependence. If I have an absolutely flat, like mirror surface, then the angle of incidence would just be the angle of reflection. But a roughened surface means a single ray comes in, it kind of scatters in every which way. And the scattering is this Lambertian profile. So this is sort of how roughened surfaces tend towards, no matter what you do, or at least if you randomly roughen them, this is kind of how they tend to behave. So we'll just take that as gospel that cosine theta is a thing. So then what you do is, okay, a ray comes in, it hits the surface, and it scatters every which way. Now I'm going to add up how much energy reaches or gets absorbed in this bulk material as all those rays scatter from top to bottom. So that's a big, horrible, ugly integral there. But you can see it's just, I'm integrating this thing in spherical coordinates. This guy here represents my transmission from top to bottom. And the 1 minus that means this is the absorption of that particular ray. And you notice that secant theta implies if I'm at normal incidence, I only go width of W. If I'm out at like 45 degrees, I actually have to travel through more material. If I'm way out here at 90 degrees, it just goes on forever and would get absorbed. So then this represents the relative intensity of that particular ray. And this all here is just the Jacobian and spherical coordinates. So another bug, this pi here is supposed to be pi over halves. If you ever get the motivation to rederive this for yourself, that's an error. So don't do that. So then you do a bunch of math and approximations. And what's fun, you can do the Taylor series bit here. And turns out you can't do this, but then you can because the integral kind of compensates for it. So we're not going to go into details. And you find for a single pass, this is how much energy gets absorbed, this 2 alpha W here. That's the fraction of the incident energy that was absorbed in the first pass. Then you just do, the next question is, okay, when it goes from top to bottom, how much energy escapes out the bottom? So you calculate the light extraction. We don't have to worry about the details here. You just get some answer. And then you ask, okay, now all this energy was absorbed and then a bunch left at the bottom. Now it's going to go back up towards the top. So how much energy is reflected into the next bounce? And you do some more approximations and rejiggering. And you eventually get an infinite series. So I'm adding all the bounces infinitely forever and asking how much energy gets absorbed in this thing versus how much kind of scatters out the top and bottom. And then you get this geometric series that converges and you solve for it. And you finally arrive at this 2 alpha n squared W term here. And if you remember now, I have an alpha and I have an absorption factor. So I can say, okay, what is the equivalent length, the path length that those rays kind of all propagated through? If I sort of average them all together into this model n slab. And you get this 4n squared W thing. So that is a popular expression you'll see in light trapping literature. They'll talk about the Jablonovich limit, the ergodic limit, the Lambertian limit, and sometimes they'll just call it straight up the 4n squared limit. So why is that significant? Well, in crystalline silicon, the index of refraction is 3.5. So you square that, you get around 12-ish or so, or something like give or take. And then you multiply that by 4, and it's as if the slab were 50 times thicker than it really is. That's kind of what this all boils down to, is if I have this 1 micron slab, but I have all this perfect Lambertian scattering in it, it would behave as if it were 50 times thicker than it really is. So that is the big thing people love about light trapping, is you're kind of pretending as if the slab is thicker than it is, and they call that a path length enhancement. So you'd say it's as if it were 50 times thicker than it really is. That's what this all finally boils down to at the end of the day. So that's why people love this Lambertian limit and why everybody tries to do as best they can to approach it. So there you go. Now you're all experts in light trapping and Lambertian scattering. So remember I told you it wasn't exactly a hard limit. It's sort of a soft limit, kind of a practical limit. There are ways of getting around it, but they always inevitably have some horrible trade-offs to them. So how much time do we have? When does the class get out? Oh, we got tons of time. That's good. Are we still recording, by the way? Okay, good. So this is a really fun thought experiment I like to throw around, because in my experience, sooner or later, you're going to work for some pointy-haired boss who's going to have all sorts of crazy ideas, and they're going to seem superficially good at first, and then you're going to analyze it and you realize that they're terrible, terrible ideas and they'll never work. So a big chunk of my career has been spent telling my boss why he's stupid and his ideas will not work. Every now and then they're smart and they'll have a good idea, but 9 times out of 10 you'll have something like this. And your job will be to explain, either make it work and show how it will work, or prove why it can't be done, or will just never practically work in practice. So this particular model here is a great example of just such a scenario. So you imagine, instead of bumping up my surface, I'm just going to have a little hole here, a square millimeter in size or less. And I'm going to put a big giant lens up front, and I'm going to capture all the light and focus it onto that little hole. And then I'm going to just cover my solar cell with metal on top. So it doesn't matter where this ray, it can bounce and bounce forever, and it's very unlikely that it'll hit another one of these holes here. And in fact, the smaller those holes and the more you spread them out, the more infinite my light trapping is going to become. So this seems like I now have absolutely perfect light trapping, right? 100%, or maybe 99% light trapping, depending on how far I can push this. So the question now is, what could possibly go wrong? Is this a good idea or a bad idea? Say what?
I don't know. You gotta have it's gonna converge to one spot. You pretty much gotta have it tracked.
That is the first obvious problem. Because if you're off a little bit, you miss your little hole. So you absolutely have to track the sun if you're going to make something like this. And that's not necessarily a bad thing. Like, there are solar stations where they have little trackers that would follow the sun. I'm sure maybe NASA does it on their little rovers, Mars rovers, right? So maybe that's an expense you're willing to absorb. But how expensive is that really? How much cost would it add to my whole system if I now have to have all these mechanical thingies following the sun? The metal layers I don't think are really bad. I think it's just aluminum. So aluminum is pretty dirt cheap, and you can do like E-beam evaporation deposition on a large area. So I would say the aluminum's not really a big problem. But the idea is the sun moves across the sky and you have to follow it. And not only does it move across the sky, depending on the season, it's going to be up or down a little in elevation as well as azimuth. And you have to have 2 axes of motion to track the sun now. Because if you're off by a little bit, just a couple of degrees, you completely lose all your energy. So that is a huge amount of complexity. And remember, the drive here to widespread adoption of solar cells is to make them as cheap as we possibly can. We need that $1 per watt. If this adds 50 cents per watt, I can't necessarily compete with coal anymore. What if it's $2 per watt now? Maybe it triples the cost of this thing, right? So that's a big deal. And so you might also look at, okay, what about the mechanical constraints of not only having to follow the sun in 2 axes, but I have these big, giant, heavy metal lenses, or not metal lenses, glass lenses everywhere. And they're all to be mounted on big struts, and it's going to be big and heavy and bulky, and that's going to add more cost. So, yeah, I got all this light trapping, but now I have this big, giant, heavy contraption. Are there any other reasons maybe why this might not be such a great idea you can think of? Remember, suppose I do all this, I can get perfect light trapping almost, right? 95% light trapping efficiency. So another question you might have to ask, compare this to is, how good can I do without it anyway? What if I forget all of that and just have a good surface? I'm still getting like 81% light trapping efficiency. So at best, I can only add 20% to my efficiency by doing this. So that means if I add any more than 20% to the cost, it's sunk. I gain nothing from doing it. Okay, and this is actually fairly straightforward to do. I just bump it up the surfaces, add a little anti-reflective coating, and this is all pretty straightforward stuff. And I can just throw away the mounting and the lenses entirely. And already I'm pretty close to 100%. And if And I don't even have to be 1 micron thick. Maybe I can make it 2 microns, and that'll add up to, say, 85%. So you have to also compare it to what you can already do without it anyway. And you see, well, there's just this tiny little smidgen of extra efficiency to gain for all this horrible mechanical contraptions and nonsense that goes with it. So these are good. I like this because it's not a terrible idea at first. It is technically correct. You can get nearly perfect light trapping, but you really have to pay for it. And you can already do close enough for all you know. So these are questions you'll have to weigh and have the insight to tell your boss, no, that's a terrible idea, or yes, that's a great idea, and here's why. And so that's why I really like that thought experiment. So that's pretty much light trapping in a nutshell for thin film solar cells and how it applies to energy and the grid. And some of this information is probably dated. I don't know how the economics have changed because a lot of these slides I made in like 2012. So I wonder how cheap silicon really is at this point. But it's still like the physics are there. They haven't really changed as far as I know. So it's good stuff. So, okay, any big questions? Yeah?
So when they report efficiency numbers, does that take into account like the actual energy of each photon that could be producing, or is it?
Yes. So here, I think if we go back to like this slide here, that 25% lab efficiency.
Right.
Yeah, that is the absolute efficiency. Here, if I make that thing and I take it outside and I'm absorbing energy from the sun, for every watt of light that hits this thing, I will get 1/4 watt of useful energy out. So it takes into account everything. You have the light trapping, which is kind of the first step. Then there's kind of your, I think they call it internal quantum efficiency, IQE. So that says, now that I've trapped the light, how effective am I at converting it to electricity? And so then there's the issues, like you say, of, I waste a lot of energy by exciting particles above the band gap. So there's internal issues like that. There's some thermodynamic issues where just the mere virtue of the thing being warm causes you to lose a lot of energy. So all told, you put all that together, and it turns out, 25-30% is kind of the most efficiency you can even possibly get given the constraints. I think if you use something like gallium arsenide or multi-layered stacked solar cells, there are various ways to get better or worse. For example, I think there's some people who do solar cells where they will stack them in different material layers. So the idea is you have one band gap here and another band gap here. So the lower energy photons are kind of being absorbed, and the higher energy will go through, or that's probably backwards. The lower energy will tend to pass through and be absorbed in the bottom. The higher energy gets absorbed, and you can squeeze out a little bit more efficiency and get to like 35% or 40% or so. There's actually a chart I have somewhere where it actually shows trends in efficiency over time for all these different kind of schemes of solar cells. So you have like the multi-layered solar cells, there's crystalline silicon, amorphous silicon, cadmium telluride, and they're all on this big chart, and some are down at like 12%, some are up at 40% or so. You probably will never see like a 40% efficient solar cell off the shelf to put on your house because they're just so complicated and difficult to make, and the materials are rare and expensive to get. So we're probably going to just see this is a pretty good practical limit that you'll see because just silicon is the way to go for most of this stuff. But like I said, if you're going to put a Mars rover up, you want to capture every last photon you can get, so you'll probably won't care about the expensive super layered kind of solar cells. You might be willing to pay for that. But on the grid, it's a different story. Okay. Any other questions? You all feel like you're experts in light trapping now? Yeah?
So the last hypothetical scenario you showed with
Oh, yeah?
Has it been tried out in the last setting just to see?
Let's see, you're talking about like this guy here? That particular thing, I'm not 100% sure. I know like there are solar cells that have done tracking. Solar concentrators were a thing for a while. I think there was like one solar cell that there was an idea that kind of competed with solar cells, photovoltaics, where they had this sort of a tube of some kind of fluid, and they had all these parabolic mirrors kind of concentrating light to heat the fluid, and the motion of the fluid was then used to generate electricity. And it turned out, those could be super efficient, but they had to track the sun in order to above 81%? Oh, in the light trapping efficiency. Technically, yeah. Theoretically, yeah, you could. Yeah, so I'm pretty sure somebody somewhere probably tried something like this. I've seen similar stuff thrown around in textbooks and papers, but I think somewhere in the back of everyone's minds they realized this would be big and bulky and insane to try and do practically. Especially, remember this layer here of silicon is only like a micron thick, and somehow you have to put a lens up here. But I'm pretty sure people have figured out a way where you have like a layer of glass on top, and they would kind of physically etch the lens into it somehow. And so I'm fairly certain that's been tried. I haven't found any papers on it, but I haven't exactly looked either. But mostly this is just to show, well, I guess to go back a little bit here. So you have this 4n squared limit here. There are, every now and then you'll actually see a 4n squared divide by sine theta, and where that theta represents the angular extent of your light source. So what happens is, if you had an absolutely perfect point source of light, then your path length enhancement would be infinite, because what you could do is go back to this thing here, and you would just have perfect light trapping all concentrated. But the simple fact that the sun is not a point source, it has kind of a finite angular extent, which means some rays are going to come from a little to the left here, and some are going to come from a little bit to the right. So there's a fundamental limit here to just how much you can focus a finite source of light. And then you have the issue of there's all this light coming from the periphery in the sky. It's actually not insignificant, but you'd give all that kind of stuff up. So it's sort of a yes and no kind of sort of back and forth. And a lot of you read a lot of the papers on it, people sort of get it, and you can tell who gets it and who doesn't quite get it. And I don't know, it's interesting, it's fun. Sorry, did I answer your question? Yeah. Okay, are there any other questions? That's all I got for today. And tune in Thursday, and we'll talk about the opposite problem of light extraction. So this is all about getting light into a solar cell. Now we want to get light out of, say, an LED. All right? Yep.